And can you hear me? Can you see the laser pointer as well?
Yes, perfect.
Yeah, great. Yeah, I would like to begin to thank Juan for the introduction and Joel and Wei for organizing this wonderful seminar series. You know, one of the best things happened, you know, since the pandemic, and Wednesday seminars, webinars is always the default thing for my group to watch. So today I'm going to talk about two recent stories from my group. One is related to the gauge ambiguities, and the other is how should we understand this mystery of vibrational strong coupling reactivities. So at Rochester, my group interested in exploring complex quantum dynamics and chemical reactions enabled by intrinsic quantum mechanical behavior. And we got interested into this new area of Polariton chemistry about 2 years ago. This is really a fascinating idea where you couple molecule with quantized radiation mode confined in a cavity, such that you can start to have electronic, nuclear, photonic interactions, and all of these start to play together, orchestra that gives you a possible way to enable new chemical reactivities. So as you all know that in such hybrid system, right, you really have to consider molecule and the cavity as the entire system, right? Not only you could have those electronic excitation on this simple diatomic molecule, for example, in this picture, you could also have photonic excitation belongs to the cavity, right? That will be the so-called G1 surface, right? Ground state for the molecule, one photon in the cavity. You energetically shift up the ground state curvature with the energy of the photon, and then these two photon jet states can start to hybridize and generate so-called polariton states, right? The up and down polaritonic states, and with the energy splitting, so-called Rabi splitting. So this really gives you a way to engineer excited state surface, right? Because by doing this process, you introduce a new minimum, new barrier, sometimes you avoid crossing a conical intersection. It really gives you a way to think about chemistry when you're having this hybrid system. And for instance, if you do laser excitation now using an instant laser promoted system to the upper polariton surface, you will have a very rich dynamical interplay among all degrees of freedoms, right? Electronic, nuclear, and photonic degrees of freedom. For example, if the nuclei are sitting on this excited polariton up state, right, upper polariton states, as the nuclei vibrates, sometimes it can visit the region where it's purely electronic excited. That means molecules in the excited state. You're having an exciton in the molecule. And sometimes you could have a pure photonic excitation. You're emitting one photon in a cavity. So it seems like the molecular vibration is mediating spontaneous emission and absorption process, just like the Weizsäcker-Wigner mechanism. But the difference is now you're using the nuclear vibration to do that instead of the vacuum thermal fluctuations. So because of this rich interplay among all of these degrees of freedom, it really gives us the way to think about, can we use this strategy to control chemical reactions, right? By changing the cavity frequency, the coupling strands between molecule and the cavity, or even the quantum mechanics state of the photon, right? These are the control knobs available for quantum optics person, but now chemists can really start to think about using these strategies to control chemical reactions. And about 2 years ago, my group started to think about this, right? We've been using quantum dynamic simulation to investigate photo-isomerization reactions, and we demonstrate that through quantum dynamic simulation, we can control the outcome of a given reaction. In this case, cis-to-trans isomerization, by changing the frequency of the photon, by changing the coupling strengths between cavity and the molecule, so you can tune the non-adiabaticity between these two, or by recycling real or virtual photons to enable new reactivities. And recently, we've been also interested in control very simple, perhaps the simplest possible reaction, where you transfer charge by using cavity, right? Through light-matter interaction, we show that you can selectively tune the driving force as well as electronic coupling. So you can significantly change charge transfer reactivity once you put those donor acceptor system in a cavity. We've been also interested to explore geometric phase effect and cavity-induced conical intersection. You put a simple diatomic molecule in the cavity. So the rotation of the molecule relative to the polarization direction of a field can supply that additional degrees of freedom. So you can even enable a conical intersection for this in this diatomic molecule. And lastly, we've been interested in this new theoretical framework, so-called polarized Fock state, where we can conceptualize how cavity is doing a molecule by shifting its minimum of its Fock state associated with a particular dipole. So with that, we can understand, a lot of different phenomena beyond the simple Rabi model's prediction. For example, we can use that to produce multiple photons and effectively doing a dynamic Casimir effect. I'll be happy to talk about each one of this after the talk if you're interested in that, but I really want to focus on two parts of the story, as I indicated in the title. And the first part is related to gauge ambiguity in molecular Cavity-QED. So it's related to a fact that what kind of gauge should we use, or what kind of form of Hamiltonian should we use in terms of describing light and matter interaction? And why do they often give you so different predictions and results? Which one should we trust? The other part is related to recent mystery of this vibrational strong coupling in Polariton chemistry. Or how should we understand those resonance effect? All right, resonance effect, as well as why could we suppress the chemical reaction rate constant, while all of this transition state theory tells you there shouldn't be any significant effect. And these are two questions I by my understanding, brought up in this webinar more than once. So it really deserves some time for a careful discussion. So let me focus on the first part, which you can find on this preprint. So let me begin by writing down the Hamiltonians. So for the pure molecule, for isolated molecule, we can always write it down as the kinetic energy operator and the potential. The kinetic energy operator includes all the charged particles, electrons and nuclei. So the index J really runs all of them. With particular mass and charge, M and Z. And you can also define the total dipole of this molecule, which is summing up all the possible charges, right? Multiply the position operator of every single charge. Again, electrons and nuclei. Now for a cavity mode, if you want to describe the quantum Hamiltonian of that, for single mode, it's simply a harmonic potential, right? So A dagger and A are the raising lowering operator for photon, or you can think about these as field operators. You can also equivalently express them as the position and the momentum operator. You can think about these are photonic position momentum, although it's not quite appropriate to think of it that way. But bottom line is, this is the Hamiltonian for the field. And you can also write down the vector potential in a way that it depends on the magnitude and then A plus A dagger. And here I'm assuming a long wavelength approximation in the sense that in principle, this A0, the field strength, should depend upon where you are in a cavity. But we're often dealing with a very larger cavity and a smaller molecule. The size of molecule is really much smaller compared to the spatial variance of the field strength. So that's why I'm always assuming the vector potential is having a constant field strength. And for Fabry-Perot cavity, the field strength depends upon the volume, effective quantization volume of the cavity, frequency of the cavity, permittivity, and it has a particular direction, polarization direction. Now, once you couple the molecule, the matter, with the cavity, this quantized mode, you have this Coulomb gauge Hamiltonian. Sometimes we call that minimum coupling Hamiltonian. Minimum coupling in the sense that it only depends upon the charge of matter, and it's basically shifting the matter momentum in this way. Under the Coulomb gauge, you're choosing basically a 0 for the longitudinal direction of A. So basically A will become purely transverse. So this turns out to be the most rigorous way to write down how light interact with matter. And this minimum coupling structure also ensures a gauge invariance structure in the sense that if you're trying to apply a gauge transformation like this, here chi is any function, arbitrary function of matter position operator, Z is charge. If you apply this gauge transformation on this Hamiltonian, you'll find that the momentum operator will be transformed in such a way, it will boost the momentum by the amount of the gradient of this scalar function. And turns out the new transformed the gauge transformed Hamiltonian will have the same structure as the previous minimum coupling Hamiltonian, in the sense that because the vector potential will transform in such a way, depends upon the gradient of this chi function. And you know that this part belongs to a gauge degrees of freedom. You can change vector potential arbitrarily, but that will not change the field or any observables. Right? So really, this minimum coupling structure ensures a gauge invariant structure. And sometimes we call that, the P dot A Hamiltonian. P is the momentum, matter momentum, A is the vector potential. So this really ensures a gauge invariant structure of the QED Hamiltonian. Now with that, we can of course do some gauge transformation and derive a different Hamiltonian. This is the dipole Hamiltonian or multipolar gauge Hamiltonian we're talking about. So this gauge transformation is a special form of the previous general version I showed you, special in the sense that this is not only a function of the matter, but also depends on the vector potential itself. You can write it down more explicitly, saying the vector potential is the transverse direction of vector potential is the field strength and then A dagger plus A. Or more explicitly, you can write down mu as sum of Zx, or write down this A plus A dagger with QC, the photonic coordinate. Remember, this kind of operator, right? The role of that is basically boosting the momentum, right? Because it depends upon the position of a given coordinate, right? So the role of that is, if it depends on a position, you apply this on a momentum operator, you boost the momentum. And here the PZW operator is basically a double momentum boost operator, in a sense that it will boost the matter momentum by the amount of this guy, ZA, and it will boost the photonic momentum by the amount showing here. And if you apply this PZW gauge transformation on this minimum coupling Hamiltonian, you get the so-called the dipole gauge Hamiltonian, or the multipolar gauge Hamiltonian. This is D dot E Hamiltonian. Sorry about the title. This is multipolar gauge Hamiltonian. So basically, it looks like this. As you can expect, this operator will shift away the momentum in the matter, leaving you a complete just matter original Hamiltonian, but it will shift the photonic momentum by this amount shown here. You can expand this PC and Q and this QC, rewrite them in A and A dagger form. These are the three terms you have. The coupling term depends upon two things: the dipole operator and the electric field. This is the transverse direction of electric field. So that's why it is commonly referred to as the D dot E term, or D dot E Hamiltonian. D means dipole, E means this transverse direction of electric field, or E dot R term sometimes. R means the position in the dipole operator. Now this guy, the quadratic term, is really the dipole self-energy. Physically, you can think about this as how matter polarizes the vacuum field and acts back to the matter. But this is really a consequence of you're applying the PZW gauge transformation operator, which will also boost the momentum of the photonic degrees of freedom, right? So it's a necessary component in order to have a gauge invariant dipole gauge Hamiltonian, as well as properly showing the right physics. So by ignoring this, we'll have weird artifacts, which we'll talk about. So as you can see, we have two choices, at least two choices to write down light-matter interaction, and they have different applications in different scenarios. Sometimes it's more convenient to use Coulomb gauge Hamiltonian, like you're writing down, you're trying to deal with a periodic system, a slab of transition metal ditractionized, right, which has the periodicity along certain direction, coupled to cavity. It's more convenient to write down or use this minimum coupling Hamiltonian, because it's easier to deal with the matrix elements of momentum operator instead of not so easily dealing position operators expectation value in this periodic system. And sometimes the dipole Hamiltonian, the dipole gauge Hamiltonian, is more convenient to write down for a molecule cavity interaction. And there are lots of examples based on that. I'm just showing you one of the earliest. So of course, as I show here, the gauge invariance should be strictly satisfied, right? So it's a very simple mathematical proof. But it turns out this is a problem really bothered physicists for decades. And turns out they do not give you the same physical observables. Or if you're trying to calculate physical observables, like quantities of energy or lamp shift or absorption, they give you different results. So before I talk about this, we can also write down the Coulomb gauge Hamiltonian in such a simple form just by using the inverse Power-Zeta-Woolley gauge transformation operator. Act on the matter Hamiltonian, so you have this boost of momentum. So you can equivalently write down the Coulomb gauge Hamiltonian this way. Yeah, but the thing is, these two gauges really gives you different results. And I'm just using a quote from a paper, early paper from Lamb and Scully, right? They mentioned that this is an outstanding problem in modern quantum optics, that if you're using two different Hamiltonians, the E.R versus the P.A, you got quite different results. Even though you can prove the gauge invariance is strictly satisfied for these two Hamiltonians, as long as you apply these two Hamiltonians to the simplest possible problem, like this 2s to 2p transition in a hydrogen atom, and calculate lamp shift, you got different results. And they started to quote Janus' comments on this, right? The whole generation of physicists has stumbled on this problem and lived not only under the shadow of which Hamiltonian should you use, right, in order to get the correct physics, but also into the deep mystery. How is it possible for a theory for the formal gauge invariance is proved easily once for all? You can lead to grossly non-invariant results as soon as you're trying to apply this to the simplest real problem, like this hydrogen, 2s to 2p transitions. And this problem, this ambiguity has been brought up many times, and there are many resolutions of these ambiguities. But to the best understanding of at least myself, it's still there in the quantum optics community. I'm just going to show you one really nice recent work by Peter Rubble, where he demonstrated that for a charged dipole coupled to a cavity, so you can really think about confining electron in this double well potential, with different gauges, you got different results, right? So with dipole gauge, you got, these are the green dots, they agree with the exact simulation. If you solve this problem numerically exactly, they agree pretty well, decently, with the dipole gauge. But the Coulomb gauge really started to break down very significantly. So G over omega C, that's a normalized coupling strength indicating the different coupling regimes, right? So in this region, 0.1 to 1, that's the ultra-strong coupling regime. But the breakdown really already show even before the ultra-strong coupling regime, right? So you can see you can start to see the deviation. And this is where a case you have a good reasoning to use two-level approximation or state truncation, right? Because you see, in terms of the matter state eigenspectrum, the two levels are really separated from the higher levels. So that's why dipole gauge, with this two-level truncation works. It faithfully describes the correct physics as if you can solve this numerically exactly. They agree. But the Coulomb gauge, if you're trying to do this two-level approximation, it breaks. And of course, this is an interesting problem. Not only theoretically, as a theorist, we definitely want to resolve this across the entire range of coupling strengths. We want to have gauge invariance structure. We want to understand the mystery. Why when you apply this to a two-level system where it should work, but they break the gauge invariance, where in general gauge principle works. But also, this is a experimentally available regime now. So experimentally, you can achieve ultra-strong coupling for light-matter interaction in Cavity-QED or in circuit-QED. So now you have those experimental conditions. It's not like back into a couple of decades ago, we don't know how to achieve these ultra-strong coupling regime. We can leave in the excuses that those regimes or those deviations doesn't matter. Now we can have experimental tests that really shows or test the validity of a theory. So this is the problem I'm really interested in, because I really want to know to what extent we can understand or write down a light-matter interaction formally exactly, and to what extent approximations taking upon that is valid, and when do they break. So of course, if you're trying to blame anything, one thing you can blame is state truncation, right? So because the
I'm
Yes.
sorry, Professor. I'm sorry to interrupt. I think we have a question.
Hello, hi, Professor. I'm sorry. So can you go back to your previous slide?
You mean this?
But this one. You mentioned that the gauge invariance will break down for this ultra-strong coupling in the Cavity-QED, because I think that which is seems that is related to this finite dimension description of the system. For example, the two-level system, as you mentioned. But I think in the two-level description of the system, the coordinate and the momentum. The commutator between the coordinate and the momentum is not exactly equal to I. So
That's
that make
reason? So the commutation relation between any two arbitrary operators can only be defined in the complete states, and the truncation will ruin the commutation relation. So the X and P commutator is no longer IH bar. That's actually how Heisenberg, right, systematically derived the result IH bar back into the 20s. But we'll talk about this. This is part of the reason. But what I'm trying to convince you at the end is, even with an explicit state truncation, I can still manage to give you invariant result between Coulomb and dipole. And that's really, like you said, deeply related to truncation, or how truncation ruins different things, right? It ruins the gauge, the commutation relation. It ruins the locality of potential. It also do a lot of weird things I will talk about. So hopefully it will be clear. Yeah.
Okay, yeah, thank you.
No problem. So yeah, one thing you want to blame is basically truncation, right? Like Zhendong already said, right? So in the full space, these two Hamiltonians are strictly gauge invariant, like we proved very quickly at the beginning. So, but often, we want to truncate the matter state with different reasonings, right? In the practical reason, higher excited state is always difficult to obtain, no matter for a molecule or for a main electron atom. It's always difficult to accurately obtain those high-lying excited states. And for physical reasoning, you're often interested in the low energy regime of the matter subsystem. When you couple to the cavity, right? So depends on the resonance conditions. Often you're only interested in a certain type of transitions, right? So that's why you often form a projection operator, for example, the ground state excited state of the matter, and start to write down the matter Hamiltonian and the dipole operator in this subspace, right? So the matter Hamiltonian, you can think about these are the adiabatic states. That means you have ground state energy, excited state energy, and then because it depends upon the nuclear momentum, nuclear position, you also are going to have this so-called derivative coupling explicitly. You can also write down the dipole operator in this subspace. You have usually permanent dipole for G, ground state, E state, and then transition dipole. They explicitly depend upon the nuclear configurations. Right, and once you plug in these quantities, and here I'm always going to use the calligraphic symbol to represent an operator in a truncated Hilbert space, in a truncated electronic subspace. So once you plug in these quantities, right, truncated matter Hamiltonian, truncated dipole operator back into this, you have this truncated version of the Coulomb and dipole Hamiltonian. And it turns out they're no longer gauge invariant. It breaks the gauge invariance. And they generate the weird result as showing in the previous slide, right? Where the Coulomb gauge seems like work pretty fine, but the dipole gauge operator or Hamiltonian really start to give you weird results at the very beginning, and with a little bit strong light matter interaction. We can blame the truncation, but we want to understand this problem a little bit better. Say, what is the exact origin of this breakdown of the gauge invariant? And so there are three different opinions, recent opinions, and being the last one is ours. I'll briefly mention this.
I'm sorry, Professor, before you continue, there's a question from Raul Tempela. You can talk now.
Hey, Frank. For me, from my understanding, I wanted to ask a question, about the truncation of the states and sort of the breaking of the gauge invariance. If you sort of translate this back to the paper by Peter Rabel and co-workers, what exactly should they do in their model in order to have these two different models or these two different representations converge?
I will talk about this row. Yes, I'm glad you asked this question. This is exactly what we worked out recently. I'll Just give me 2 more minutes, you'll see it.
Sure, awesome.
All right, so the reasoning, the origin, right, for this gauge invariant problem, you know, break down the gauge invariant problem from Peter Rubble and their work, they're basically pointing out that X and P operator are fundamentally different. There's a fundamental asymmetry between X and P. If your potential is not harmonic, then they're different. You know, based upon Heisenberg equation motion, you can write down the matrix elements of P and X in such a way, and you'll see that, you know, the P matrix elements related to X matrix elements multiply the energy gap between these 2 states. So that means for an X operator or mu operator, mu is really, the dipole operator is really the charge multiply position operator of electron, right? So, or charged particle. It turns out the largest matrix elements only belongs to the nearing neighbors, and that's why truncation in the dipole gauge works well, right? Because that only gonna allow transitions among the nearest neighbor states, but it doesn't work well if you're trying to use the P operator or, you know, in a P dot A Hamiltonian. The reason for that is you see the matrix element of this P not only depends upon the magnitude of matrix elements of X, but also depends on energy gap. So you can imagine that where, for example, from the 0 state to the 3rd state, we have a weak transition, right? You have a weak transition by the dipole or by the X operator, but that will be compensated by a very large energy gap. And in a sense that, such that the whole thing is actually larger. So basically the truncation in the P space, right? Or you know, the state truncation in a P dot A form Hamiltonian doesn't work as well as in a D dot E form. And the P dot A, the P matrix elements always trying to make a transition to a higher state because you are having a larger matrix elements. That's absolutely true. And that's basically explaining why, you know, even the dipole gauge Hamiltonian works good, the Coulomb gauge Hamiltonian really breaks down very easily. But that doesn't help us to really try to resolve these ambiguities. I'm being a little bit greedy than Peter Rubble here. I'm trying to say, if I have to make a state truncation, absolutely necessary, just because I don't have the capacity to obtain very accurate excited state. I have to make this truncation. Can I still manage to make invariant structure of Hamiltonian between the Coulomb gauge and the dipole gauge? So this is what I'm trying to accomplish here. And of course, you have to find the other origins or possible origins. Another origin recently pointed out by Savastra and Nori is basically this. Once you have a projection, you're gonna break the locality of the potential operator, right? So this is, you can think about as external potential. If you have more than 1 electron, these are the Coulombic interaction. So once you have the projection, it turns out it's no longer a local operator in the sense that if you visualize, for example, this double well potential, right? If you visualize the matrix elements of this double well potential projected by a certain matter states, electronic states, along X and X prime. So these are the position bases. Only when you have incredibly large number of matter states, you do recover a local structure of this potential, which is a double well. I'm having a negative sign here. If you're only truncating the states to be 2 or 3 levels, this becomes non-local, right? So it's not purely diagonal. So in the sense that this Vx prime is no longer a delta function. It's having some value. So it breaks the locality. And you can really formally think about this is now an operator of X and a P. P is giving you that non-local part. And if you have that, then it's really bring a lot of trouble, because the truncated Coulomb Hamiltonian, you can, for this guy, you can write it down as the P projection operator act on the original Coulomb Hamiltonian. You can write it down more formally as P act on this inverse PZW operator, act on a matter Hamiltonian, then sandwiched by another P. For the kinetic energy, that is fine. That's whatever it is. For the potential, it's problematic in a sense that, based on their opinion, right? It's problematic in a sense that if you apply this gauge operator first, then because this is a local potential, right? The PZW operator boosts the momentum, matter momentum, right? But it will not touch a pure position operator. So in a sense, you're going to recover this V operator. And once you do that, you project this P on V, you have a non-local potential. So in the sense that if you're doing this procedure, you're ended up to have a non-local potential, but this non-local potential has not been properly gauge transformed by the PZW operator because you apply PZW first on a pure local potential. So they're suggesting this non-locality issue is really the cause of the gauge non-invariance. And their solution is very simple. So project this operator, matter potential operator first, and then apply this projection also on the PZW operator, and the whole thing should give you a gauge invariant Hamiltonian. We are having disagreement with Nori. I'll tell you what I think. Our conjecture is related but different. Our conjecture is this. If you look at the matter Hamiltonian, the dipole gauge Hamiltonian, you see that every single operator is properly confined in the subspace P, right? So if we're doing projection for the electronic states, you can think about you're reducing the dimensionality of the Hilbert space by changing from the complete electronic subspace into a projected electronic subspace. You're doing this projection. And if you look at a dipole operator, every single term is properly confined in P subspace, right? So including this light matter interaction term and this dipole self-energy term. And we hypothesize, we conjecture that this is no longer the case for HC. For instance, we are using this UP or PU operator, right? And you can easily show that this is not properly confined in the P subspace. It contains Q, right? You have an identity sitting here. You can write it as a P and Q. So you have some operators in Q. So we conjecture that the gauge non-invariance, or the weird result you see in the projected or truncated Coulomb gauge Hamiltonian is due to that some operators, once you do this procedure, are not properly confined within the P subspace. And some of them actually start leaked from the P into Q. And this is also the case for the PUP operator suggested by Nori, right? If you write it down in the Taylor expansion, you have some terms not properly confined in P. For example, this mu square, right? The P, mu squared P, you can insert an identity, right? Which is the electronic identity P plus Q. You naturally see there are some Q components. So in that sense, none of this actually properly confine all the operators within the P subspace. If you are thinking about a special example, you can also see that immediately. If you're thinking about two-level system, or two-level atom coupled to a cavity, right? You can write down the truncated Coulomb gauge Hamiltonian in such a way. This is your d.E term, and this is your dipole self-energy term. So the coupling strength really relates to just one transition, right? 0 state to 1 state related to its dipole. That's fine. But the diamagnetic term, it's a constant. So it doesn't matter what kind of truncation you're using. And you immediately realize that this actually includes every single possible transition based on the TRK sum rule, right? If you have this sum rule, you can rewrite this diamagnetic term as possible sum of all the, starting from a particular state J to all the possible state K. So it includes all of these transitions. In that sense, this diamagnetic term is really counting for all the possible states that's making a transition to, right? So this is basically leaking outside your proper confined subspace P into Q. And the fact is, if you can also do a truncation in this D, arbitrarily saying, I'm not gonna do this full sum, but I'm gonna only include this mu01 transition as included in G, you can drastically improve the result. You don't get the exact result as HD, but you got very close result, a significant improvement. So this really gives you some sense that, or the origin, or lets you speculate the origin of this non-invariant structure between Coulomb and dipole gauge Hamiltonian under the truncated subspaces, because when you do the Coulomb gauge, not every single one of the operator is properly confined in the P subspace.
Professor Hu, we have a question. We have two questions, actually.
Hi, Frank. I have a question about the Rabel and the Nori pictures. Aren't they very related in some sense?
They are related, but they're trying to blame the non-locality, the breakdown of the locality of the potential as the source of gauge non-invariance. We're trying to say this is because not every single operator is properly confined in P. They're related, they're not exactly the same.
But I just want to, can you make a, can you emphasize the distinction between the Bernardi's picture and the Savasta picture?
Oh, these two pictures.
Yes.
So this is right. So basically, the Rubble picture is trying to say X and P are fundamentally different if you have a non-harmonic potential, and hence you naturally requires more states to describe a Coulomb gauge Hamiltonian P.A structure. You just need more states to converge it properly. The Silvestre-Nori picture is saying if you can properly treat the non-locality of the matter potential and also apply gauge principle on that, you'll be able to fully resolve it, even with explicit state truncation, the same two-level truncation.
Wait, so for example, with the Nori picture, may I understand? So I mean, if you just naively apply the projection operator, then okay.
Oh, I see. The picture here, this is the potential. I'm basically visualizing the operator in the x and x prime axis, right, in a position Hilbert space, right? Once you apply projections, say P include 2 states or 3 states or 200 states, and how do the matrix elements of this calligraphic V looks like in a position Hilbert space? So that's basically this picture. The Rubble picture is basically
so that induces momentum couplings in the yes, Nori picture.
You can think about this due to the momentum, or you know the incomplete or the incompleteness of electronic states, right? So that ruins the pure locality of a potential.
I see. Thank you.
All right.
So Frank, I also had a question. This is Roel. So what you're saying about the dipole self-energy term, essentially incorporating, you know, all the possible electronic states.
Not the dipole self-energy. This is diamagnetic term. This is.
Oh, sorry. Okay. Okay, right.
Different dipole self-energy.
Is it conceivable, or in other words, are you saying that you know, depending on the truncation, that term may dominate over the actual linear photonic electronic coupling term?
What I'm trying to say is, in a proper treatment, you should have a diamagnetic term, a square term, sure. The problem with this is when you are trying to, you know, think about using a inverse PZW operator on the dipole back to the Coulomb, right? That operator in the full space is basically shifting the matter momentum, giving you that a square term. That's a constant. But once you project it, a constant will not be projected into the proper subspace. So that's why it effectively contains more than it's supposed to be. That's why you see it include all the possible states as a final states to make a transition. Mm-hmm. Now the question is, if you can carefully trim out all the other terms related to Q, can you restore the non-invariant result between these two Hamiltonians? And that's exactly what we discovered.
Mm-hmm. Okay, thanks.
So what we discovered is, you know, based on that conjecture, is if you manage to properly confine every single operator within a subspace P, you will be able to have invariant quantities predicted by both Hamiltonians. So in that sense, you can construct a PZW operator in this way. So the projection should be on the mu operator inside this momentum boost operator. In the sense that if you do Taylor expansion, you see that every single term is properly confined within a P subspace, right? Because, you know, no matter what's the power here, the mu is always within a P subspace. Here I'm just reminding you what was going on in the full space. Now, based upon that, you can also define what is the Coulomb gauge Hamiltonian in the truncated subspace, right? So remember that in a full space, you know, we can mathematically write down the minimum coupling Hamiltonian as the inverse momentum boost operator act on the matter Hamiltonian. plus the photonic Hamiltonian, right? Here we're going to define in an analogous way with this full space Coulomb gauge Hamiltonian, now in the truncated space. So in a sense that you're going to truncate the matter Hamiltonian, but also you're going to apply this truncated version of PZW operator. Very easily you can show this is indeed invariant from truncated Coulomb Hamiltonian, in the sense that you just have to apply the forward PZW operator on both sides, right? And the U will combine with U dagger, that's gone. U dagger combined with this U, that's gone. Basically, you have a pure truncated matter Hamiltonian, and now you're going to have this U photonic Hamiltonian U dagger, which will boost the photonic momentum by exactly this amount with truncated version of the dipole. And that's exactly the dipole Hamiltonian in the truncated Hilbert subspace I showed you before. So in that sense, this new Coulomb gauge Hamiltonian will provide exact same observables as the dipole gauge Hamiltonian, even with the explicit state truncation. If you want to do two-level truncations, that's totally fine. With this Coulomb Hamiltonian, you're going to have the same result. Whereas compared to the original Coulomb gauge Hamiltonian, right, you always have this terms being outside subspace P. Here, we're confining every single term within the subspace P. So everything is fine. Now, of course, this is not very convenient. It's a general expression. It's very compact, convenient. That means often it's not very useful. We want a more detailed expression of HC. What is that? So to do that, you really have to work out, this explicit gauge transformation, applying this new PZW truncated operator on, the matter Hamiltonian, right? And we can do that by starting with a momentum operator, and based on the BCH identity, you can show that it depends on an infinite series of commutators. And the first commutator can easily work this out. You know that immediately. That's the negative gradient of mu. Here I'm defining mu operator in the truncated Hilbert space as this function. In principle, it's also a non-local function. It depends on both x and p in principle. Right? But nevertheless, I can write it down as I can work out this commutator and with the result of this. How about the higher order terms? Right now, I don't have a closed form, but I can at least denote that as a residual momentum, P tilde. I will call that the Taylor-Mendel residual momentum. The two authors, my students who convinced me that exists and is not zero. And right now, we're just going to denote that as P tilde. Right? It's a typical trick for theorists, hide complexity by definition, through definition. But you also have to notice that, what Nori told us, right? The projection will break the locality. So in principle, you have to denote that as a potential with both position and momentum in a truncated Hilbert space. With that, you can easily derive what is this truncated Coulomb Hamiltonian. You'll see that for the momentum part, it depends upon this transformation, right? Not only it depends on the canonical momentum, but also now you're carrying a gradient, negative gradient of mu operator multiplied by the vector potential with this residual momentum. And the and the matter potential is whatever it is in a projected form, also inverse PZW transformed by this operator I defined here. So that turns out to be the Coulomb gauge Hamiltonian in the truncated subspace that still generate the same physics as the dipole gauge Hamiltonian in the same truncated subspace. And compared to the original form of the P.A Hamiltonian, you immediately realize that instead of just depends upon the a square or contain terms up to a square, this Hamiltonian contains an infinite order of a through this residual momentum as well as this Coulomb version, this matter Hamiltonian in truncated space. So in that sense, if you want to do a proper truncation, not only you're changing the matrix elements of P, but also you profoundly change the structure of the like matter interaction. And of course, this will go back to the original minimum coupling Hamiltonian in a complete basis limit. In the complete basis limit, this mu function becomes the mu operator. The gradient of that mu is simply just charge, and here the gradient of mu becomes a charge. So basically, you're having a minimum coupling Hamiltonian, and then the corresponding Coulomb, the corresponding potential, right, in the complete basis. So you're going back to the original Coulomb Hamiltonian. But you see, the truncation really also changed the commutation relation. Like I said, the commutation relation can only be defined within a complete space, which resulting in this structure, right? So which, by having a minimum coupling structure, you really ensure gauge invariance, like I showed in the beginning. But now this gauge invariance structure is gone, right? So it's no longer a simple charge multiply A, but a gradient of mu multiply A, and carrying this residual momentum. So in that sense, you do break the gauge invariance structure. You do ruin a general gauge invariance in the sense that you no longer have a minimum coupling structure in your Hamiltonian. But still, this Hamiltonian managed to generate the same physics in a truncated space connected through this truncated PZW operator U I defined. And it will be very convenient if you really have to use a Coulomb gauge to describe light-matter interaction. For example, a periodic system coupled to a cavity where you want to use P operator to describe light-matter interaction. And that will require exactly the same amount of matter states to properly describe the physics, and actually it will use a little bit fewer Fock states to describe, to convert your result. And we believe you can also use this in a different context, like classical light and matter interaction. So basically, you just have to replace the vector potential, the quantum mechanical version of vector potential with the time-dependent fashion, but you better do it in this Coulomb gauge Hamiltonian instead of the original truncated version of Coulomb gauge Hamiltonian. And of course, I can also show you how to work it within a molecular system. It's easier for us to separate the Hamiltonian between the electronic part and then the nuclear kinetic energy operator. And then you can carry the same derivation, and you ended up to have the result like this. Bottom line is, you do have those informations from electron structure calculation. No matter this is adiabatic states or diabatic states, you can properly compute the matrix elements, and then you can plug in back into this Coulomb gauge Hamiltonian. We even derive an analytical result of this, and I'm going to show you in a second. So it looks like this for a two-level molecule coupled to a cavity, and we can consider a Shimetu type of charge transfer model where we can do exact simulation. We can also strictly diabatictize this model Hamiltonian so we can have strict diabatic states. The bottom line is we can now have a simplest possible molecular system, compare the results from different gauges, right? The Coulomb gauge Polariton eigenspectrum defined this way. I'm taking out the nuclear kinetic energy from the total Hamiltonian, and I'm computing the eigenspectrum by changing different R, right? The Coulomb gauge gives you this result. The dipole gauge gives you the solid line. The Coulomb gauge breaks the results very early on, as we see from that simple one electron confined in a double well potential, right? And then if you do the truncation properly, the new Coulomb gauge Hamiltonian really gives you an invariant result as a dipole gauge. So I do think this will bring a new framework. If you absolutely have to use a Coulomb gauge to describe light and matter, it resolves the ambiguity between these two gauges. With the interest of time, I think I'm going to move on to the second part of the talk. And I think Joel has a question.
Yeah, there is a question from Matt.
Sorry, Frank, can you go back?
Go back to...
No, just to the last slide you were showing.
Okay.
Which is not this, right? Yeah, here. Okay, so PR was this Taylor-Mandel.
Yes, you got it.
But that was very ugly, and now you have an analytical result, but that's just because you have a two-level Hamiltonian. Is that correct?
That's truncation, and that profoundly changed the way light and matter interact with each other. Now, you have to consider, how this PZW operator in a confined space gonna act on the momentum, right? So that not only gives you the gradient on mu, but also this additional higher order commutators.
Wait, but why were you able to resum all of that exactly, or was it? Because I mean, in principle, this P of R is very difficult, isn't it true?
Yeah, in 2 levels, it turns out you can write down everything in a Pauli matrix, right? Representation, and you know, if you sum up all these terms, all the higher order commutators within this BCH identity, you'll find that they are the Taylor expansion of this term. So you do have an analytic answer.
Can you show again the expression of that of P of R as a summation, as an infinite summation?
It's an infinite summation, yes. So if you Taylor expand this cosine sine.
Yeah, but do you mind showing that your slide the first time you show that expression?
It's not in my first slide, so it's in the support information of the paper. I can send you that online soon. Yeah, but it's quite tedious, and I really appreciate Mike sorted out the Mendel-Taylor sorted out analytically. Now beyond 2 levels, that's why for 2-level system we do have an analytic answer. Beyond 2 level, how do we have an analytic answer for that? I don't know. Or would we be able to have an analytic answer? I don't know. Maybe we can borrow some other tricks. You can use these so-called Gell-Mann matrix. Represent arbitrary matrix, right? Beyond 2 levels, maybe there will be some complicated form. We can manage to do that. At least we can try 3 levels, but I don't know. For the time being, I don't know. And this it's a natural consequence for truncation, and this will go away if you are in a special representation of mu operator. So if you're in the eigenstate of mu in the truncated subspace, then you can explicitly show that this residual momentum is gone, because mu becomes pure diagonal and all the higher order commutators are gone.
Okay, so then the last question that I would have is, what is the advantage, or may you compare, say, this Hamiltonian that you have produced and the one that Savasta and Nori are suggesting to use?
One advantage I can think of is, if you're dealing with periodic system, a slab of transition metal distructurized coupled to cavity, right? It's not convenient. The dipole operator itself, the expectation value of dipole operator or position operator is not that well defined in a periodic system. It's much more easier for you to start with P.A Hamiltonian. The question is, how would you be able to achieve the same level description, same convenient description as the D.E? That's one aspect. The second aspect is, like I mentioned, turns out this is closely related to the Polariton transformation of a dipole gauge Hamiltonian, which is also related to the polarized Fock state we recently discovered. So it will reduce the number of Fock states in order to converge the result. Because in a dipole gauge, your field operator is not displaced by the matter. The only coupling between light and matter is carried through this momentum coupling, right? So only here. So basically, you can use only a few Fock states to converge the result. That's another advantage numerically. And then for some method development, like I remember a method that Pranahar talked about a couple of webinars ago, where she started with a P.A Hamiltonian and use this ANSAs to do variational calculations. So sometimes it's also easier for you to derive method or develop methods based upon a P.A Hamiltonian. So there are cases where you want to use P.A Hamiltonian more than D.E. But like I said, I want to get to the bottom of this, not because it's practically useful, although it is. It's more related to a mystery. Why, in principle, they are gauge invariant, but apply truncation, it breaks it. How should we understand it? How should we fix it? It's more like a mentality of a theorist rather than the practitioner calculation performer. But nowadays you do have experimental setup that allows you to test when 2 levels are good, you can still achieve ultra-strong coupling. In those cases, we really have to seriously dealing with this non-invariance between different gauges, and I think this is just the beginning of that work.
Okay, thank you.
Yeah, for the time of interest, so I'm curious how much time do I have exactly? I really want to talk about the other part of the story, which is related to the vibrational strong coupling in Polariton chemistry.
How long do you think it would take?
I can take it as short as probably 5 to 6 minutes.
That's okay, I think. 5.
Yeah.
That's great. That's exactly the time I'll need. Okay, so basically we're talking about, we speculating this is purely a kinetic effect, and you can understand this rate constant reduction from a very old theory, so-called Hamiltonian theory, and this is a regime, so-called dynamic caging effect. Let me just basically tell you what experimentally they find. So the Anderson group and their coworkers basically trying to confine a large amount of molecules in a cavity, in a microcavity, and their picture is, you know, the vibrational excitation start to hybridizing with with the photonic excitations. You have these Polartonic states, and of course you're going to observe that strong coupling, collective strong coupling from absorption spectrum. You see the splitting. They're asking the question: will this light matter interaction, right, vibrational strong coupling, translate into chemical reactivity? And it turns out it does. So basically, if you tune resonance of your cavity to a particular vibrational frequency, you can see you slow down that reaction, breathe constant, and you often see a resonance behavior, right? Resonant behavior, where you can change the frequency of the cavity, and it turns out the rate will be achieving a minimum value at a particular frequency. This frequency is close to that vibrational frequency of a particular bond. And you can see that resonant behavior beyond just simple example. For example, in this reaction, or in enzymatic hydrolysis reaction, or in a recent cyclization, right? I'm not organic chemist, but you see this behavior show up in more than one reaction. So give or take, you have to believe the existence of this resonance behavior. So when you couple molecule resonantly with a cavity, you know, you tune the cavity frequency in resonance with vibrational frequency, it seems like it slow down the reaction, and you will see that. In terms of theory, we don't understand it at all. There are many of them. I'm just selecting 3 of them. They're suggesting, you know, based on the transition state theory analysis, you don't see that slow down. There is no significant fact. In this different study by Johannes, so he basically considered a simple single molecule coupled with the cavity. He suggests that you will see some modification. So basically, through this D.E Hamiltonian, right? So this is the cavity or photonic coordinate interact with the permanent dipole molecule, and because the position dependency of the permanent dipole, right? In this model, the permanent dipole is 0 on the dividing surface, and permanent dipole is has the largest value in the reaction and product region. So you do see a large difference as you increase light matter coupling strength. So he does see modification, and he does see a significant change of rate constant. It's a slowdown because as you turn on the light matter interaction, you will see the top of the barrier and the bottom well energy difference start to increase. But he doesn't see resonance effect. This, you know, as you change omega c, you don't see, you know, what you have in experiments where you have a particular minimal rate constant at the particular frequency of the cavity. And we're trying to understand why this is going on, or what could be the possible origin for this resonance effect. And by no means I'm trying to claim that this is the ultimate answer for this mystery. And I don't think we'd resolve it, but I would like to share some perhaps fresh perspective in terms of understanding this resonance behavior. We're considering the same model as Johannes. So basically this is the Shin-Mei-2 model coupled to a cavity. So basically you have transferring electron and a proton here. The reaction coordinate is that proton. And the difference is we do consider dipole self-energy, which will shift the photonic position operator. So this is actually the so-called polyphase Hamiltonian. And if I'm visualizing the potential shaded with these blue terms, I have a potential like this. I'm visualizing the potential not along the QC, the photonic coordinate, but also along the reaction coordinate. It looks like this. And the bottom line is, once you consider the dipole self-energy, you're not going to change the barrier height as you claimed. I'll show you in a second. So the two key frequencies you have to remember here is the bottom well frequency omega 0 and the top of the barrier frequency omega b squared, which is the imaginary frequency and denoting the real value of that, or the positive value of that Hessian. So what I'm talking about is basically this. If you properly consider the dipole self-energy, what it does is it gives you a complete square. So basically, it will only displace the potential or the problem along the QC direction. No matter how strong the coupling between light and matter is, you're going to only displace that, not changing the relative barrier height between the bottom well to the top of the barrier. So in that sense, that if you're trying to count the barrier change between these 2 points, that's not changing at all. It's the same barrier, potential barrier. So in that sense, in TST, there is no change of rate. But the rates, TST is only approximation. There are corrections, and that's from purely dynamical corrections. You can formally write down a rate constant as TST rate, transition state rate, multiply this so-called transmission coefficient. You can probably define that with this so-called flux side correlation function, and you can then compute that. Based upon this cavity Born-Oppenheimer surface I showed you, you can speculate in that the light-matter interaction doesn't change the barrier height, but it does significantly change the topology around the transition state region, right? So in that sense, it could possibly change this kappa, the transmission coefficient, which characterize to what extent the reactive trajectory will recross the barrier. Here, I'm treating every single degrees of freedom classically, including this photonic degrees of freedom, because this is really a low frequency cavity mode in the same range of the vibrational from nuclei that we often treat classically. So I'm doing everything classically. And I can compute the transmission coefficient and find that as you increase the coupling strengths, you do decrease the transmission coefficients, which means you're going to eventually decrease the rate. Also, you see more and more oscillatory behavior of this transmission coefficients. If you visualize these reactive trajectories on top of these cavity Born-Oppenheimer potential, you see that in a low coupling regime, you're basically having a so-called non-equilibrium salvation regime where the photonic coordinate doesn't impede the crossing of the barrier of this reaction coordinate that much. So you can roughly have the same transmission coefficients as before, right? So in this regime. But once you're increasing the coupling strengths, enter into a strong coupling regime, you start to form a solvent cage. Solvent cage in the sense that if you're thinking about photonic degrees of freedom as a solvent, you're forming a cage such that you're trapping the reaction coordinate within the solvent cage, and it will recross many times before it escapes from the transition state region. That's why it leads to a decreasing long time plateau value of kappa, as well as increasing the oscillatory behavior of this kappa. This turns out to be a classical textbook example of solvent caging effect. By textbook, I really mean I find a similar picture from textbook, this textbook by Brown-Peters. So you see the exact same picture if you have the real solvents and your reaction coordinates, right? These two pictures, as well as what that solvent coupling to the reaction coordinate does on the transmission coefficients as we see here. So in that sense, the cavity mode, low frequency cavity mode, is actually acting as a solvent, as effective solvent degrees of freedom, such that it's forming a caging regime and slow down the chemical reaction. And of course, you can compare with experiments. It's not very meaningful because we're not doing the real calculation as the molecules used in experiments, nor we're doing more than one molecule. But even with that, if we somehow capture the essential observations in experiments, at least telling me that I'm having, by chance, correctly to the right direction. So you can compare with the rate to the experiments. We see slowdown as you increase the coupling strength. If you want to translate the coupling strength, if you want to translate that slowdown of the kappa, right, the transmission coefficients into a effective couplings, into effective barrier height, this is what you got. And of course, the coupling strength we have to use here in this particular model has to be very large, but it roughly captured the essential observations in the experiments. You can also have a proper understanding of the resonance fact from this. So here, because we're having a very simple system, not only we can do the numerical simulation, we can also sort out this kappa analytically. And this is a very old theory, so-called Heinz theory. You can analytically derive the transmission coefficient in this way. So it depends upon the barrier frequency, the cavity frequency, and then the coupling between the cavity and the dipole, the slope of the dipole on the dividing surface. So in the sense that this analytic expression will have a minimum at this value, and this value will be close to the top of the barrier frequency, where your coupling strength is not significantly larger than the barrier frequency square. So if you print out kappa, right, you will see that as you increase the coupling strength, right, the minima do shift, but you do see a resonance behavior. So basically, this resonant frequency will be close to the top of the barrier frequency, and that's our explanation for this resonant behavior observed in those experiments. In comparative experiments, yeah, this is what you see, right? And we can also properly understand what's going on, again, by printing out trajectories on top of those cavity non-member surface, right? So here we're changing the coupling strength, not necessarily the frequency. So basically, we're maintaining a proper normalized frequency. We're changing we're maintaining a proper normalized coupling strength. We're changing the frequency. So as you change the frequency, you're changing basically how wide is this parabola, right? From the very wide to some sense narrower, where you have a caging effect, to even narrower here, indicated by this D. So this is where you're really stretch this potential significantly. And so that you don't have a caging region anymore. Instead, you're having a tubing region where it's extremely narrow. The reactive trajectory almost follows straight paths, and going through that, and you start to alleviate the caging effect. That's why you see an increase of the rate.
We have a question from Professor Rafael Ribeiro.
Hi, Frank. Well, thank you for this very intriguing talk. First question here is there no temperature dependence in the transmission coefficient? And a second question would be, if you added more cavity modes to this description, so other near resonant modes, how do you think that these results would be changed?
So yeah, good question. So temperature dependency, not classically in this case, but we speculating in the quantum regime, you probably will. We're treating everything classical. This is an intrinsic classical theory. More than one mode in your cavity, right? If you consider that, I think you can still apply same analysis. So in that sense, you just have more than one effective solvent mode, right, coupled to your reaction coordinate. You probably see the similar effect.
But do you think that there would be any changes to, significant changes to the magnitudes of these effects when?
Could be.
Because like a cavity has an infinite, in principle, a large number of available modes, right? And also, if you add dissipative effects, have you guys thought about how that could influence some of these results?
Yeah. So all these far mode, dissipative, non-cavity mode, or more than one cavity mode, they are basically just effective solvent mode, right? So the story here I'm showing you, the result I'm showing you, does not relies on light matter interaction forming these collective hybridization states. It basically is suggesting that once you have a resonant photonic mode, right, it acts like a non-Markovian solvent mode. So you can slow down the motion of you can slow down the reaction rate by forming this caging. If you have more than one of these modes, very likely you're going to enhance this behavior. You're going to start to form a multidimensional cage, right? So further slow down the recrossing, or further enhance the recrossing and slow down the rate constant. As for the for those leaking modes, non-cavity far field mode, it's basically a mode or coupled to a cavity mode. We haven't thought about this very careful, but I think it will probably just add on additional fault. Based on the intuition we have in chemistry, right? You have solvent, you also have other co-solvents mixed with the other solvent, coupled to the solvent, you probably enhance or the effect of recrossing. Things like that, but we haven't had a chance to sit down and probably do the theory or do the simulation.
Sure. Yeah, I mean, I think it would be quite interesting to see how some of these results depend on temperature. I mean, because those experiments, they do report a temperature-dependent kinetics, right? And then in principle, they ascribe to changes in activation energy or even the reactivation factor and so on.
That's true. So they have temperature-dependent delta H and the delta S. Here, where we're only having temperature dependence from delta S, if you want to translate that into an Aryan type equation. But in terms of delta G double Dagger, they extract delta G double Dagger from the temperature dependence, right? Where they reported like here. Here, I'm translating my kappa into effective change of delta G double Dagger. It seems like this can already achieving those changes as observed in experiments, right? So those are the temperature dependence we're talking about. But where they use the temperature dependence rate to extrapolate delta H and delta S.
Yes, and I would suspect that the transmission coefficient does have a temperature dependence in a realistic calculation, right? Because it's going to be dependent on the thermal population of the cavity modes or other modes that are going to determine the configuration.
Absolutely, yeah. So, but this is like where we're doing a very simple classical treatment for the cavity mode, and this very simple theory. And of course, if you can properly quantize photonic degrees of freedom, it should depend on temperature, and we'll have a more appropriate understanding of the precise temperature dependency. We're working on that. Good news is we're theoretical chemists. We do know a lot of tricks to quantize photon, right? I probably don't have time to mention that, but we're working on it.
Sure.
Just like quantizing nuclei, right? So for us, this is nothing more than additional nuclear degrees of freedom or additional solvent degrees of freedom.
That makes sense. Thank you.
Thanks.
We also have a question from Professor Shedong Shang.
Hi, Frank. So thanks for your quite intriguing theory for explaining this behavior, the deep observed in the experiment. But how do you think about the role of the energy fluctuation induced by the vibrational modes? From the Marcus Joyner theory for the electron transfer, this fluctuation is quite important to understand the behavior of the reaction rate.
Oh, that's true. That's true. So if you want to think about it in that way, versus the Joyner theory is basically saying, if you consider explicit state-to-state transition, right, vibronic states to vibronic state transition, right, you have all these channels, right?
Yeah, I'm sorry, the molecule cavity coupling will could influence a lot the energy fluctuation of the molecules, right? Yeah, and then which might be one of the reasons why and could explain why the experiments can observe this dip in the reaction rate. So how do you think about that?
Right. So what you're essentially saying is, by considering the quantized states of this matter and cavity coupling, right? So basically, you think about classical trajectory in this two-dimensional space. That's basically where the classical trajectory leaves, right?
Mm-hmm.
Based on the classical treatment I showed you, this light-matter coupling doesn't change the potential barrier when you're reaching from the bottom of this two-dimensional well to the top of the barriers. In that sense, it doesn't change the TST rate. What it does is basically also reshaping the topology in the transition state region such that you're forming a cage. Classic.
Yeah, but it may change the fluctuation of the energy on the in each potential well.
Can you properly?
I mean, the molecule cavity coupling can change the energy fluctuation in each potential well. So will this influence the reaction rate?
Not the TST rate. In the at the TST level, it doesn't. When you properly consider kappa, it does. When you properly if you're dealing with really a non-adiabatic reaction like charge transfer, it also does. I can show you why at the beginning, at the end of the talk, probably. So if you think about the light-matter interaction, right? In the D dot E form, right? So basically, that's more like a mu operator coupled to A plus A dagger. So you're gonna have like a photonic coordinate coupled to mu, and that show up in the off-diagonal matrix elements if you only write down your Hamiltonian in the donor-acceptor diabatic states. So in that sense, you know, the cavity mode is more acting like a fluctuation, like you said. Yeah? So if you consider the fluctuation of off-diagonal terms, so it will add up on top of the static donor-acceptor integral, or coupling.
Exactly. Yeah, and then that will influence the reaction rate.
That's true, and matter of fact, you know, we actually showed this. So let me probably conclude this. I'll go back to that briefly.
Yeah, I'm sorry. I'll just allow one more question, and remember that you can always post your question in the chat, and then maybe Professor can answer it after the presentation is finished. So allow Jorge to talk now.
Yeah. So to bring a brief summary, so this part, you know, what I'm trying to tell you is, you know, based on our very limited understanding, the VSC kinetics modification is really originated from the non-Markovian behavior of the cavity radiation mode. And once it's coupled to the reaction coordinate Q, it forms a solvent cage that slows down the chemical reaction rate. And the resonance condition for achieving this minimal reaction constant is where your cavity frequency is close to the top of the barrier frequency, not the same as the condition you achieve in the IR spectrum or transmission absorption spectrum when you are trying to measure the bottom of the well frequency coupled to the cavity. So that means, you know, that lets us speculating, you know, would this be a new strategy for solvent engineering, right? For example, you can think about cavity mode serving the same role as a solvent, but you can change the frequency. That's good news. You can engineer the frequency of this solvent for free, right? I mean, easily, not for free, but much easier. So would that be able to allow you to change a lot of the reactions, right? Like simple organic reaction, you know, enzymatic reaction. And turns out these are the early cases for solvent engineering. And the interesting fact is, the Anderson group also focused on these reactions and turns out to show similar effect. What that means a selective transformation for synthetic chemistry, or what's the best scenario to use this strategy? These are the open questions. For the theory side, you know, we really need a theory beyond a single molecule, which will also explain the collective coupling fact. And we need to treat a cavity mode quantum mechanically. We do know how to, and we also need to have a more realistic description of the molecule. But I would say that the equal challenge is also laid out for the experimental side, right? If you can manage to achieve a single molecule coupled to a cavity plasmonic cavity like this, then based on our theory, our prediction is you'll still be able to see this resonance change or resonance slowdown of the rate with a resonance frequency that's close to the top of the barrier frequency. Okay, a brief summary is, you know, I basically talk about the gauge ambiguities between the two gauges, Coulomb dipole gauge, and we provide a proper resolution for that. And hopefully this will be useful practically in terms of describing light-matter interaction when you have to use Coulomb gauge. And we provide an interesting, hopefully interesting vibrational strong coupling theory to understand the recent experiments of this resonant behavior of slowdown of chemical reaction rate. We're speculating that the cavity mode is acting like a solvent degrees of freedom, and by coupled to the reaction coordinate, it forms a solvent caging effect that slows down the reaction rate. Back to the question that Jen Dong's asking, we do know how to quantize proton or nuclei with extended phase space description. We can apply the same strategy to photonic degrees of freedom. So we're using this path integral ring polymer representation to quantize not only the nuclei, but also the photon coordinate. We do find that the fluctuation you're talking about can be properly understood and quantized in this way, and also understand why it will enhance the charge transfer rate. You can really think about now the cavity mode is serving the fluctuating component. This is, I think, called Pierce coupling, right? In the off-diagonal elements, so we can enhance the rate constant. We do see that, and that agree very well with the full quantum treatment. We're also working on bringing a more realistic description of the molecule by using this on-the-fly simulation, this method we developed, so we can have a realistic simulation of real molecule coupled to cavity and understand or simulate Polariton photochemistry through on-the-fly simulations. So with that, I would like to thank my group who did the work I mentioned. So arXiv, Mendel, and Mike Taylor, the Taylor-Mendel residual momentum mentioned on that gauge invariance paper. Wang Huai as well on the fly simulations. Shutirsta on the spring polymer quantization I showed you, and Xin Yang recently on the explanation of the ground state BSC reactivities. Marlon and postdoc working on these geometric phase effect and conical intersection and cavity, and generous funding from NSF. Without that, we cannot do any of this. And special thanks to my program officer, Abby Gofield. She's retiring, giving her a big applause for that, supporting our research. My collaborators, Todd Cross, Nick Malvikas, and then valuable discussions with all of this, especially Peter Maloney, Joe Everly, Nazir, and Sylvester. Computational resources and other funding resources. So thank you so much for listening, and thank you so much for having me, and I'd love to open up the floor and answer any additional questions.
Thank you very much, Mr. Franco. I have a question from Jorge. Jorge, you can have.
Yeah, can you hear me?
Yes.
Oh, so thank you for this very informative talk. And I would like to ask you, what are your hopes of taking your model for the chemical reaction to the collective regime? Because, so you said that in order for this to work, you need the topography of the potential energy surface to change significantly. And this is something that is mentioned in Johannes Fass's paper, that this can be achieved in plasmonic cavities. However, in a Fabry-Perot cavity where strong coupling is achieved through a collective mechanism, this doesn't seem like an achievable goal, because the changes for a single reaction, a single molecule reaction, don't actually seem to capture all the collectivity of strong coupling. So I don't know if you could comment on that.
You're absolutely right. So to us, collective effect is still a mystery. We don't understand that properly, and we try to use this. We try to use your normal mode representation in the collective regime and try to let that collective mode couple to the cavity, right? So basically, we're trying to retranslating what we learned here in that normal mode representation. Turns out that would be a really weak effect. The resonance structure is still there, but the modification is really weak. The reason for that is in the collective VSC regime, right? The cavity interact with molecule, and the coupling strength between molecule per molecule with the cavity mode is really weak, right? And that doesn't show up in the normal mode or collective bright mode. So to us, collective coupling is still a mystery. If you really want to push this explanation in the most naive way to many molecules, you are missing, we don't have a good explanation for the collective coupling. But the resonance behavior is still there. It's just weak. And you still have, you know, a small rate constant showing up when the frequency is close to the top of the barrier frequency. So you're absolutely right. And like I said, by no means I claim we fully understand it. I think this is just the beginning. My only hope is, you know, this could turns out to be totally wrong, but at least, you know, I'm opening up some room for the further discussions to invite more people in this mystery so we can properly resolve that and provide an ultimate theory, you know, in the near future.
So, okay, I don't think there is any more questions. There are some questions in the chat, but if you agree, Professor, can I send those questions to you? Maybe you can address them.
Absolutely.
Those who ask the question can look for the answer once we upload the YouTube videos. The answers are going to be in the comment section of such video. So thank you very much, Professor, for a very nice talk. If you allow me to share my screen just to make a last announcement. Yeah, thank you very much. So I just want to say that next week, our next panelist is going to be Professor Hannah Zamsel from University of Heidelberg, who is going to be talking about pumping exciton polaritons via luminescent sp3 defects in single wall carbon nanotubes. So thank you very much, Professor, again, for a very great talk. And I hope to see you all next week for next Polariton Chemistry webinar. So have a good day.